This is an experimental photovoltaic thermal panel being tested for the all-electric sailing yacht Zero. The goal of these panels is to provide all of the power needed to run the yacht's auxiliary systems while it is at anchor. Welcome to Foundation Zero. We're a platform that promotes the use of renewable energy by openly sharing insights and data from a range of innovative engineering projects. In this series, we're following the creation of Sailing Yacht Zero, the first all-electric yacht of its kind, and the ways in which it's pushing the boundaries of renewable energy. One of these boundaries is generating renewable energy while the yacht isn't sailing.
Well, the only way basically is solar power. And since the surface area that you have available to install solar panels is limited, and you just have your deck, you have to make best use of every square meter of power that you have available. So my name is Bob van Zomeren. I'm a physicist, and I was asked with the Zero project to help with the in-depth physics of the engineering of the Zero project. The solar power that falls on any surface, depending on where you are in the world and what kind of weather it is between 500 and 1,000 watts. And if you want to allocate, let's say, about 70 to 100 square meters on a yacht like this, then the amount of solar power that you have available is between 35 and 100 kilowatts. That's it. You have to live with that. Now, the conversion efficiency of just photovoltaic is about 20%, 25%. So then you would be left with not enough power to power the hotel load of the ship. So you have to use the other power that is also coming on the surface, so the other 80%. And the only way you can use that is by using it as heat. And if you harvest heat, you can harvest the heat at 40 degrees centigrade, and then it's relatively low quality because you can't do a lot with it. Maybe you can shower with it, but that's about it. And if you harvest it at higher temperatures, it's useful for other applications as well, such as, for example, absorption coolers. They require an input temperature of about 60, 65 degrees, and then you can cool with the heat that you've harvested. So the conundrum with PVT is that you want the heat at a high temperature, which automatically leads to that the photovoltaics is also at a high temperature. And it means that your photovoltaic efficiency drops because the photovoltaic cells have a lower efficiency at higher temperatures. And that's kind of a conundrum. You gain heat, but you lose electricity, or you gain electricity and you lose heat.
In addition to this balancing act is the fact that PVT panels are not commonly used at sea. So the team began designing and testing custom solutions which would address both theoretical and practical constraints.
And one solution that we came up with is that not the entire part of the solar spectrum is useful for the photovoltaics. Only about 60% is useful for the photovoltaics. And the other 40%, no matter what you do, the photovoltaics cannot convert that into electricity. So you could filter that out before it hits the PV. And if you use a filter that is a liquid, so for example, water mixed in with a substance that absorbs that part of the solar spectrum, you could use that as a pre-filter. So we built a system that actually does this, and it worked relatively well until we came to the conclusion that there are two engineering setbacks in this point. The first is you need a relatively high pressure to circulate the water and put water pressure on a large surface that generates large forces. So the pre-filter, which is basically two sheets of glass, that would start to expand, and we had to stop the experiment because otherwise the glass would have broken. Then we circulated with a somewhat lower temperature, and we came to the conclusion after a couple of days that there was algae growth in the liquid, in the water, which was a mixture of water and glycerol. No matter what we did, we used distilled water, we added a little bit of salt, but the growth still kept coming up, and that's the thing. Life finds a way to live in places where you don't expect it, and it covers your entire PV panel, so that wasn't a solution. After we decided to not work with the pre-filter solution, we were still left with the idea of using PVT panels that have a relatively high output temperature of, let's say, 60, maybe 70 degrees. And that means that you have to insulate the photovoltaic from the environment so that it doesn't lose heat in the environment. On the back side, it's relatively easy, but on the front side, it's a little bit different because you want all the sunlight to enter and hit the PV and at the same time have a good thermal insulation. And there are solutions where you have a sort of very pure, optically pure silicone. It's called Silgard, it's made by Dow Chemical. And that is used for aerospace applications, so it's very resistant against all kinds of chemicals. It has a low index of refraction, and it's basically a rubber. So what we set out to do is make a mold that is covers gas in front of the PV panel, and that gas takes care of the thermal insulation. Also, that worked really well. There's one disadvantage with this silicone rubber, and that is it gets dirty very quickly. The other thing that was a problem is, since it's silicone, the attachment to the metal is not very good. So we had this mold on a PV panel that worked really well, but after a year of testing in the real world, we saw that the silicone detached from the PV. So we set out for another in the market available solution that does good thermal insulation while letting in a lot of light, and that's vacuum glass. It's basically double glazing, but then not with argon or other gas in between, but simply nothing in between. It's vacuum glass. It's relatively thin, it's about 7 millimeters thick. It lets in a good amount of light. It's an off-the-shelf component. You can buy them and specify them to size. And we mounted that in front of a PV panel. And that actually works a little bit better than the Silgard, because the thermal insulation value is better. But a lot of the vacuum glass that's available in the market isn't just thermally insulating vacuum glass. There's also an optical coating on it that is there to prevent heat from thermal heat from going out. But it also prevents thermal heat from coming in. So that made that the thermal insulation value was very good, but the performance of the PVT panel was a little bit less than that of the Silgard, because not all the heat from the sun was let in.
Various configurations of the above solutions were tested in the lab and real-world environments to get a holistic picture of which one held the most promise, not just for performance but for longevity as well.
So the parameters that you want to match with each other is, first off, of course, what is the electrical and thermal performance of the panel. The other thing that's also very important is how well can we manufacture it. And the third thing that is important is how well is it going to perform over its lifetime. If it works well right now, and we can actually manufacture it right now, but in 5 years' time it starts to degrade, then we don't have a solution either. So those are the three things by which we have to judge what we're going to do. And at the moment, the vacuum glass in front of a standard PV panel would be the best solution.
We will revisit this topic in a future video once we have more data. But before we wrap up, here are some final thoughts on why heat harvesting is so important in the first place.
When we tackled the problem for the first time of making a yacht that has 0 fossil fuels, is that you first have to look at the energy balance as if it's a balance sheet with line items. And the first line item, of course, that you tackle for your efficiency is the biggest one. And we figured that the biggest one would be the thermal energy usage, so cooling and heating. And we've done our best in all possible ways to improve on that balance sheet line item. And we had to do that because the challenge was to do something with 0 fossil fuels, not with a little bit or a backup generator, with 0 fossil fuels. And it means you have to really scrutinize every line item in your balance sheet. And previously that was never an issue, because you don't realize that a tank of diesel, 2,000 liters of diesel, is an enormous amount of energy. And once we started to say, well, but we're not using any fossil fuels, 0, then you realize how precious energy is actually. And also how it's very well possible with existing technologies and properly designing the system to cut back on a lot of line items without sacrificing comfort.
Foundation Zero maintains an open source policy with all of our learnings. So, if you're interested in diving further into this project, please visit the website where you'll find more information.